So, we have just looked at case 1 for a body at rest. Then let's look at case 2. A body in motion. Please don't forget, all these divisions are coming from the first law, because the first law they says the body will either be in state of rest or uniform motion. Okay? That the one which is at rest will tend to remain at rest, and the one which is moving will always tend to continue moving. We have already analyzed the one which remains at rest. That the reason why it will only tend to remain at rest, it is because when the force acts on it, it will be equal and opposite. Now, let's look at the one which is in motion. So, we can say a body can only change its velocity if and only if an external, a body can change its velocity if, let me just say that, if an external force is applied. A body can only change its velocity if an external force is applied to the body. Okay? That a body always have to remain with its velocity, not until an external force is applied, either to change the velocity by increasing it or reducing it. Otherwise, the body will move with a constant velocity. And if the body is moving with a constant velocity, it is in a state of dynamic equilibrium. What do I mean by dynamic equilibrium? It is a state where the body is moving, but the forces in the direction of motion is equal to the force opposing motion. Because equilibrium is all about saying that if a body is in equilibrium, that means that the forces pulling the other side is equal to the forces pulling the other side. And that can happen when the body is at rest. That is what we call static equilibrium. The body is not moving. And again, it can also happen when the body is moving. And that is a scenario of a body moving with a constant velocity or zero acceleration. It will be in a state of what we are calling dynamic equilibrium. So equilibrium can be when the body is moving or at rest. Okay? So when we say a body can only change its velocity if an external force is applied on it. And then I can say otherwise, if the velocity is uniform, i.e. zero acceleration, then there is dynamic equilibrium, and the resultant force in each direction is 0. Okay? So in a scenario where a body is moving with the constant velocity, it is in a state of equilibrium, but that equilibrium is what we call dynamic equilibrium. Equilibrium when the body is moving, but still the force in the direction of motion is equal to the forces in the opposite direction. So we can have an example here and say a body of mass 2 kilograms is acted upon by forces shown below to make it move with a uniform velocity of 10 meters per second. So if I have that, let me draw it in this free space here. They are saying this is 8. They are saying this is 15. And now I have x there. And then I have here 3 newtons. And then they are telling me here there is 10. And then here there is y. And then here there is 12 newtons. And then I'm saying find the value of x and y. Okay? So, we are saying that, please don't forget this, that the moment a body is moving with uniform velocity, forces in the direction of motion is equal to forces opposing motion. We shall clarify more about that when we come to the Newton's second law. But still, the truth is, a body moving at a constant velocity is in a state of equilibrium, in that it is no longer increasing the speed, it is no longer reducing the speed. That means that what is the other side is equivalent to what is it? Because if what is in front is bigger than what is behind, it means the speed would increase. Also, if what is in front is less than what is behind, that means that resistance is too much, the speed is supposed to reduce. But in a scenario where the speed is neither reducing nor increasing, it means the force in front is equal to the force behind. And that is what we are calling equilibrium. But which type of equilibrium? That is dynamic equilibrium. Equilibrium when the body is moving. So, we have an example here that a body of mass 2 kilograms is acted upon by a force shown below to make it move with uniform velocity. By the fact that the body is moving with a uniform velocity, that is enough to tell us that there is a state of equilibrium. If there is equilibrium, forces in opposite direction should be equal to 0. So, let's solve this and see. I'll say, for uniform velocity, okay, there is dynamic equilibrium. Therefore, I can say forces to the left should be equal to sum. I'm saying sum of forces to the left should be equal to sum of forces to the right. To the left, which forces are we having? We are having 8 plus 3 should be equal to x plus 15. Is that okay? So if I'm having that, I'll now therefore say that I have here 11 is equal to x plus 15. What is my x? My x is 11 minus 15. And x should be equal to negative 4 Newton. Now, the trick behind is, what is the implication of the negative? Okay? The negative is that x is supposed to be equal to 4 Newton to the left. The reason why we are getting negative, it is implying that for this body to be in equilibrium, x is not supposed to go in this direction. Instead, x should be in this other direction. And that is why we are getting it as a negative. So it is implying that x is supposed to be 4 Newton, but it should act in the direction to the left, if at all we are to have equilibrium. And then let's attack vertical direction. We can also say upward forces should be equaling to downward forces. And that means that upward force we have 12 should be equaling to downward force is 10 plus y. That means that 12 minus 10 equaling to y. That will take us to y equaling to y is equaling to 2 Newton. So you say, therefore, y is 2 Newtons downward. So if we get it as a positive, it implies that it is very true that y is supposed to go down. But if we had gotten it as a negative, it would imply that the force y is supposed to act in the reverse direction, like we have done to x. That we got x as a negative, the implication was that it should act in the opposite direction. And if I say to the left, I should no longer write the negative here, because the negative is implying the direction which is to the left. Now let's meet for the next part or the next law of Newton.